Okay. I think we are looking at the first theorem of calculus. I probably made a mistake there. I think I did not give a proper formal proof for it, so I thought I will do that. I'll do that first. Then I was thinking, if there is a first theorem of calculus, is there a first theorem for geometry? Is there a first theorem for algebra? Is there a first theorem for arithmetic? I thought I'll just check, just out of curiosity. See, many times curiosity is a good thing, because I didn't find those, except for trigonometry. There is no officially, what people say first theorem. You can call any theorem as first theorem. For example, you can call Aryabhata's declaration of Jya and Kotijya as the first theorem of trigonometry if you want. It's up to us to say that. But in any case, they never agreed on it. So I thought first thing I will do is, let us define a first theorem for trigonometry. Then I will tell you what people have defined as first theorem of arithmetic and algebra. Finally, we will come to the first theorem of calculus, which anyway, I said I will revisit because I did not give a proper, formal, rigorous proof for it. Okay. So we are with trigonometry now. What is the first theorem for trigonometry? My idea was that you can use the Pythagoras himself. So sin squared x plus cos squared x is equal to 1, which is universally true for any value of x, correct? Any real value of x, this is true. So you can treat that as first theorem of trigonometry if you want. But then I found, if you look at Pythagoras theorem, that was not even the first theorem of geometry. Actually, it was Thales theorem. So what is the corresponding theorem of trigonometry which corresponds to, which is the same as Thales theorem, is actually a by sin A is equal to b by sin b. This is so symmetric and beautiful and so easy to remember. You don't even have to by heart it. So a by sin A equal to b by sin b equal to c by sin c. Now you can see if the angles ABC are the same in another triangle DEF, the same angles are there, obviously sides will be in the same proportion. You can see that. Actually, this is Thales theorem. So we can treat this as first theorem of trigonometry. That is one. Next we come to arithmetic. In arithmetic, what can be a theorem? You might think this is on what is known as factorization of numbers. That is, arithmetic basically has got to do with natural number system. 1, 2, 3, 4 up to infinity. That we are handling those numbers, and you take any number, we can break it down to factors. Unless it is a prime, of course. If it is a prime, we can't break it down further, so that remains a prime. Non-primes can always be defined as products of smaller numbers. So what is the combination is a question, and we want to factorize in terms of primes only. That means, what I am saying is, if you have a number 20, for example, I can write this 20 as 2 multiplied by 10. I don't want to write it like that because 10 itself is not a prime. So we factorize that further. So you should really write that as 2 multiplied by 2 multiplied by 5, right? So, which is actually 2 squared multiplied by 5 to the power of 1. So this is a factorization. So when supposing we factorize a number any n, the theorem says there is only one unique way of, one and only one unique way of factorization of any number. That is the theorem actually. So you can't factorize 20 in any other way other than having 2 2s and 1 5. That's it. In terms of primes. So factorization of primes is the theorem for arithmetic, first theorem for arithmetic. Then we come to geometry. Now geometry, of course, we had the two theorems earlier, Pythagoras and Thales, but then historians have, mathematical historians have decided to give due honor to Euclid, I think, saying that we have to honor Euclid by saying he was the inventor of first theorem. No? But unfortunately, there is no theorem there. So what they said was whatever the axioms that he wrote, the first 5 axioms of Euclid's Elements, which are so simple, which are obvious self-truths. Axioms, like I discussed earlier, axioms are introduced. They are not proven. They are just introduced as true, and they should be self-evident. Anybody looks at it saying, yes, it is correct. There is no question of doubting an axiom. It should look like that. And based on the axioms, you can prove everything else in a rigorous way, assuming the axioms are true. And what are the first 5 axioms of Euclid's geometry? That is known as the first theorem of geometry. What are those? I'll state those, very simple. First axiom is any 2 points in a plane. Take any 2 points. Any 2 distinct points on a plane can be joined by a line segment. You can try a line. That's it. That is the first axiom. It's obvious now. I don't think I have to prove it. Wherever the points are, I can join them with a line. That is the first axiom. And what is the second axiom? If you have a line segment, we have a line segment, which is joined 2 points, it can be extended indefinitely in either direction to infinity. That's it. I can go whatever length I want. I can extend it in either direction. That is the second axiom. And what is the third axiom? Is all right angles are congruent. That means I may have a right angle here, which is 90, what we call 90 degrees. I may have a right angle somewhere else on the plane. No? It simply says both are congruent, both are equal. No? That means I can take this and place it on the other one. It will match both the lines. That's the meaning of congruence. So 2 right angles are congruent. That is the third axiom. Then we have a fourth axiom which brings in a circle definition. If you have a line segment, any line segment, we can always draw a circle with one endpoint as the center and the other endpoint on the circle. That means that will be the radius. Line segment becomes the radius of the circle. It says I can draw a circle. That's it. Now, what you do with the circle is next. But the axiom says you can always draw a circle given a line segment with one endpoint as the center. It doesn't matter what you do with the circle. Like I said, if you have a line segment, you can always draw a circle with one endpoint as the center of the circle and the circle passing through the other endpoint. This is there. Then we have the last postulate or axiom of Euclid, which is also known as the parallel postulate, is we have got a point, given a point, some point is given, and a line segment is given, and a point is not on that line segment. Of course, it is separate from there. Then it says that we can always draw one and only one unique line parallel to the given line through the given point. That's it. We can draw a parallel line. That's the meaning of, or that is the axiom, fifth axiom. And these 5 axioms together are treated as first theorem of geometry. That is fine, no problem. Now we come to algebra. Algebra, I want to do a special treatment. That's why I took it up last. No, algebra has a first theorem, and that theorem itself has changed over a period of time. So there is an old version of the theorem. I'll state that first. And there is a new version of the theorem also. The old version is as follows. Any n degree polynomial. Now, we should be very careful about the statements in mathematics because everything has got to be very accurate. Now, when you say what is an n degree polynomial, as an example, I can write an x to the power of n plus an minus 1 x to the power of n minus 1 plus etc. plus a1 x plus a0. This is general way of writing nth degree polynomial, n degree polynomial or nth degree polynomial with the coefficients an minus 1 all the way till a0. They are the coefficients. We are saying they are real values, that is real coefficients. Now, when I say nth degree polynomial, an cannot be 0 first of all, because if an is 0, then we are not talking of n degree polynomial, we are talking of n minus 1 degree polynomial. That is the first conclusion. That's why I am saying it will be very accurate when you make a statement like n degree polynomial. Similarly, a0 cannot be 0. You are wondering why. Because if a0 is 0 and we are looking at the roots of the polynomial, what is a root? Root is a value of x for which the polynomial value goes to 0. When you evaluate, the value will become 0. So that becomes an equation. Equal to 0 is the equation. So if you solve this equation, if a0 is 0, obviously x equal to 0 itself is a root of that equation. It's like a trivial root, you know. X equal to 0, everything goes to 0, right? So obviously a0 cannot be 0. In which case, actually if a0 is 0, we won't write the polynomial like this. We'll remove x as a common factor and write that as a n minus 1 degree polynomial. Correct? No? Second aspect. No, that means, so we have drawn just by this statement, nth degree polynomial or n degree polynomial, whatever you want to call it, right, is an is not equal to 0. a0 is not equal to 0. These two conclusions we can make just by that statement, you know. Then there is one more conclusion I want to make. I don't want to look at negative values of an. An could have been negative, easily can be minus 1, minus 10, minus 1 million also. I want to look at only the case of an greater than 0. In case an is negative, we can always multiply the entire polynomial by minus 1 and equal to 0, the root won't change, of course. So obviously we get the same roots when you multiply by minus 1. So without loss of generality, I can assume an is greater than 0. So now, so what is the theorem? Now this is the observations we make just when we make the statement, I have an nth degree polynomial, correct? No? So what is the theorem? Theorem says, this is the old version. Old version of the theorem says, any odd degree polynomial has at least one real root. That is when n is odd. N is even, I don't know. It may or may not have a real root. When n is odd, definitely 100% certain there will be at least one, if not more, real root. Okay. Now, we can give a proof for it. I will give you a short proof which is more of a intuitive kind of proof, not a rigorous proof, so that you understand why odd degree polynomial should have one root, right? We'll give that. Then I would like to revisit the same first theorem of algebra at a later time, where we can look at it in a more rigorous way, slightly later on. I would like to do that. So, why is it odd degree polynomial has at least one real root is the question. No? So now, we have already deduced that an and a0 are not 0. We have assumed an is greater than 0, correct? No? So I can rewrite this polynomial, if you call it fx, I can rewrite it by taking a common factor of x power n. I can take an x power n itself as a common factor. Supposing we take an x power n as a common factor, what will you get inside? 1 plus an minus 1 by an and x, correct? Plus an minus 2 by an x squared plus etc. Last term also I can write a0 by an x power n. Now, the reason I wrote it like that is Here we wish to take the value of x and take it towards infinity. What happens in the limit when x goes to infinity? You can see the inside terms, regardless of what they are, an anyway is not 0. So an minus 1 divided by n is some real number divided by x, and that x is going up to infinity. Fixed number divided by x goes to infinity goes to 0. This also goes to 0. In fact, every one of these terms other than the 1 goes to 0, correct? No? Only 1 will be left. So therefore, the limit will be the same as an x power n, which of course goes to infinity. I mean, I am not doubting that it goes to infinity. I am only saying that the limit of this fx is decided by only the first term. We don't care about all other terms. It depends on only the first term, correct? So now we take x. X can go to infinity in two directions. No? So x can go to minus infinity or it can go to plus infinity, correct? Now this odd degree comes into the picture. Supposing n is odd, what happens to x power n? That is, x power n is either x or x cubed or x power 5 or x power 7, odd power of x, no? So when you do that, what happens to the value? How much is that? Negative. So it goes to, so fx goes to minus infinity. Whereas when x goes to plus infinity, fx goes to plus infinity, correct? You understand? So fx, when x goes to minus infinity, this fx goes to minus infinity. When x goes to plus infinity, fx goes to plus infinity, correct? No? You agree on that? So now that means if you say this is my x-axis, I won't even bother showing where is the beginning of y-axis. I don't even bother. This fx starts somewhere in minus infinity and goes towards first plus infinity, correct? No, this is the direction of f. This is the plot of f. If you look at the graph of f, it has to cross the x-axis at least once, I am saying, minimum once, because it has to go from minus infinity to plus infinity. It has to cross x-axis at least once, or it might cross it multiple times also, or it can cross it 3 times, or it can cross it 5 times. It can cross it odd number of times, basically. That is what is, in the case of an odd degree polynomial, it crosses the x-axis odd number of times. Minimum odd number is 1, so it has to cross at least once. Therefore, it has got at least one real root. That is the conclusion. Now, just out of interest, let us look at an even degree polynomial. Even degree has got x power n, which is x squared or x power 4 or x power 6. Whether x is positive or negative, x squared is always positive, x power 4 is always positive, x power 6 is always, even powers of x are always positive. Therefore, fx goes to plus infinity, whether x goes to infinity or minus infinity. Either case, it goes to plus infinity only. Therefore, even degree polynomial, if you plot, if this is the x-axis, it can start from plus infinity and go to plus infinity, which means doesn't touch x-axis at all, 0 times. Or if it touches it, it has to twice, or it can do 4 times and so on, correct? So it's got even number of roots. Basically, it's got even number of roots. Of course, there is one special case where it intersects the x-axis only once. That means it comes down, touches x-axis and goes above. Possible. This is also possible. In this case, what we call it is, actually there are 2 roots there. Both roots have the same value. It's known as a multiplicity of roots. Same root multiplied, same root again, once again the same root, you know. So this multiplicity might be a bit difficult for you to understand right now, but when I revisit the same example at a later time, I'll show you that shortly later on. I'll explain the meaning of this multiplicity also, but in general, you can see that even degree polynomial crosses x-axis even number of times, therefore may not even have a single real root. Whereas odd degree polynomial will always have at least one single real root. So that is the old version of first theorem of algebra. So now we go to the next. Our important topic of the day, that is first important topic of the day, is the first theorem of calculus. Now here, I think what we missed was what is the part of definition and what is the part of the theorem. No? So that is the, I think that is the problem that you are also going to face, because we have to be very careful about what we are defining as an integral, what we are defining as a definite integral, what we are defining as an indefinite integral, what we are defining as a derivative. These three definitions you have to keep in mind. So let us assume that I have got one function fx which necessarily has to be continuous over a closed interval, call it a comma b, and differentiable in the corresponding open interval a comma b. So that is there, is as given. We will also define a new function, I will just call it capital Fx, as the indefinite integral. So what is the definition of this? Indefinite integral can be written, representation, how we write on paper is to write this elongated s of fx dx, one form. Other form is actually we show that as a limit, as a value integrated from and to, no? So 0 to x. 0 to x, there is an independent variable which is changing from 0 to x. So that cannot be x itself, so we may have to write f y dy or something. I may have to introduce a new variable, actually the same fx dx only. Or we may decide to write that as 0 to x of fx dx itself, with the understanding that what I have written as x and dx is the independent variable that we integrate. Once integration is completed, now we take 0 and x as the actual value x up to which we want to integrate. So all three are fine. So this is the representation. And what is the definition of this indefinite integral? Is the area under the curve of fx, under the graph or curve, whatever, under the graph of f of x from 0 to x. That is defined as fx or integral fx dx. That's the definition. So which means if you look at the graph, this is the x-axis, and I got a 0 here. The value x that I am saying is some x. Obviously, since we are interested in the area under the graph up till x, this x must be inside the interval over which it is inside the domain, obviously, inside the domain. So I will put a and b somewhere on either side of x. So we are saying when I plot, actual plot may be only from a to b, possible, it's quite possible that behind a, f may not even be defined, but I am still defining area under the curve from 0 to x, which means one way is assume that the value which is not defined is 0 only. That means we will take that as 0 value. Assume the value of x is 0 up till a. Simple assumption. So we are still saying from 0 to x is the area that I am talking of. So that means we draw a line over x and say that is the area. This area, if a is behind 0, then we will get the entire area up to 0. Otherwise, we may get some partial area. It doesn't matter actually. It makes no difference. Area is defined as the indefinite integral. This is the definition of capital Fx is this area, correct? So now, definitions are complete. Now we look at the theorem. So what is the theorem? Theorem has got two parts. I will state the part 2 first. What is part 2? Area from A to B. That means area under the curve from A to B. This entire area, which is, how do we write that? Representation of that is from A to B of fx dx. This is a definite integral. Remember, that was indefinite integral. This is a definite integral definition. Area from A to B is written as A to B of fx dx. So we write it is simply equal to fb minus fa. This is the second theorem. Now that is very obvious from geometry. So you always depend on geometry for this. Now B is a point, I draw a line. So I got one area from 0 to B, which is basically the black shaded area and the green shaded area together. Now that is the 0 to B is FB. Now by definition of the indefinite integral, the area from area of this black shaded part plus the green shaded part is defined as the indefinite integral, and that is the value is FB. That is the definition, right? Similarly, the area from 0 to A, which is nothing in this case, is the definite integral FA, correct? Understand? And you subtract the two, obviously you get the area in between. So part 2 is straightforward. There is no further, it's obvious, I don't have to give any further proof for it. Statement itself is a proof practically. Now part 1 is a tricky part. Part 1 says, it says f is anti-derivative of fx. That means, what it really means is that derivative of the indefinite integral is the function itself. Is another way of saying that. That is, I can write that down. D by dx of integral, indefinite integral fx dx is fx itself. That's why it's known as anti-derivative. F is called anti-derivative because f prime, this also means this is fx now, and d by dx of fx is f prime x. So another way of writing the same thing is f prime x equal to, both statements are same, yeah. Son-in-law is daughter's husband, no? So son-in-law, daughter's husband. So like we say in our whatever respective languages, f prime x equal to fx. This is the first part of the theorem of calculus. Now how do we prove that is the question, right? So we write one small diagram which is slightly different from this, and I will show you the proof for this. Then after that we can get on to the more interesting aspects of things that I want to really discuss today. Okay. So we write the usual graph. I got the x-axis here. And we have the graph of f. I'll write that as monotonically increasing just for understanding the geometry when we compare some areas. But then it may be decreasing, or it may be below x-axis, or it may be to the left of y-axis. All are possible, in which case the algebraic signs of the expressions will automatically take care of those situations. So let me take a point x on the x-axis. This is our x. And what is this height of this? Is fx, obviously, because that is what I have plotted. I have plotted f. This is a plot of f actually, correct? Plot of f. Now we will increase x by a small increment. When I say small, it can be very tiny. It is our delta neighborhood, but for visibility purpose, for you to see, I have written it as quite a wide margin. We can call it delta x if you want, or you can call it delta, or people call it h. H is another notation. Maybe I'll use a new notation because that's what you are likely to see in some of the proofs. Or we can write delta x only. We'll write h. Okay, h. H is this distance. And we drop what is the value of function f at this point? Different, obviously. Because it was monotonically increasing, f has increased the value. Otherwise, it could be below also. It's quite possible. Now, I am interested in computing the area of the strip. I've got a strip now between x and x plus h. Correct? 2 points. So, from x to x plus h, what is the area of the strip? Correct? There are 2 ways of calculating that. What are the 2 ways? One way is we draw one horizontal line here and another horizontal line here and join this rectangle. So now you can see this area is area of this rectangle. What is that? Right. F of x is the height multiplied by h. H multiplied by f of x is the area of this rectangle, perfect rectangle. But that unfortunately is not the area that I want to look at. I have got one additional piece there now, which is going above. So I will give a name to this piece, this area. Area of this small triangular piece that is not triangle, because f can be a curve there. Whatever, there's some small piece. I will call it error or something. Call it error. Therefore, f of x plus error is the area of under this between of the strip, area of the strip is one way of calculating. There is another way equal to, we got our indefinite integral fx which has been given, which is from 0 to x plus h. I got one area. From 0 to x, I got another area. When I subtract the 2, I get the area of the strip. So, is equal to f of x plus h minus f of x. Correct? Both ways. Both are fine. So, now we do some balancing, transposition, balancing. I will take my interest eventually in proving something is equal to fx. So, let me take fx on one side and take everything else to the other side. Simple, one way of looking at it. Later on, you can work out other way of transposition, doesn't matter. So, what is fx equal to? Take everything to that side. So, error has to go that side and h has to go that side, right? So, I will get f of x plus h minus f of x divided by h minus error divided by h. Correct? No? Simple. No problem. Now I want to take the limit. Obviously, we are looking at limits. If you want any derivative, you need to look at limit. And what is the limit is for our this point to approach x as close as it wants without touching it, right? So that means h actually goes to 0. H is our delta x, which has to go to 0. So I want to take the limit, and when the h goes to 0, what happens to fx? Fx has no h anyway. Fx is fx only. Doesn't change. There is no change on the left hand side. Correct? Fx equal to. So this will be limit of f of x plus h minus f of x divided by h as h goes to 0, one part, minus limit of error divided by h as h goes to 0. Now I can't substitute h equal to 0 here because when h equal to 0, error is also 0, is a 0 by 0 format. I can't substitute. Even here actually I can't substitute, but I can take a limit. And this limit itself, remember, is the definition of our derivative. This is derivative. Actually, this is f prime x. Definition of derivative is f of x plus delta x minus f of x divided by delta x as limit as delta x goes to 0. So this is f prime x, no problem there. So now we have to look at this limit now. What is the limit of error by h? You can see error is a small piece of area here. From geometry, it is very clear this error must be less than that rectangle that you see there. Correct now? You understand? So that means error is less than, I will write that as a modulus because we might have this algebraic sign problem when the area may be negative, this side, that side, all are possible. So I am looking at the absolute value of this error. I want to compare with the absolute value of the area of that rectangle that you see on top. Correct? And what is that rectangle? Has got a width which is h multiplied by, and what is the height? Height is increase in f, no? I can call it delta f modulus. Right? So this limit, if you want to look at, this limit itself, limit error by h as h tends to 0, I will evaluate that separately, equal to or less than or equal to, it's actually less than, but when h actually becomes 0, it becomes equal. So I am writing less than or equal to modulus h star delta f divided by h. And when h is not 0, I can definitely cancel the 2, will be delta f. And obviously delta f, that is the height increase of f. When h goes to 0, delta f goes to 0. So this becomes 0. So eventually fx will be equal to f prime x. That is the limit. So that is the first part of the theorem of calculus. In fact, theorem of calculus is important. It is actually called the first theorem. Reason is our interest in calculus was not in differentiation. Not finding derivative is not our interest. Like I showed you some couple of examples of computing volumes. Our main interest in life will be always in integrals. Will always be in finding definite integrals. In fact, that is what is going to be our objective. But unfortunately, definite integral integration depends on evaluating the indefinite integral at 2 points and subtracting. No? So evaluation of the indefinite integral becomes the problem, and that is not a very easy thing to do. Saying how do you area under the curve you cannot compute very easily. It's not easy. Whereas finding the derivative is a very straightforward technique of applying the limits that we have seen. We did differentiate or derive many known functions like algebraic functions and trigonometric functions, exponential function. I have shown that. That is a simple method. So the method is to derive or differentiate as many known functions as we have and form a table of the two functions. That means, let me just make a very small table to show you what I am talking about. So we make a table. One side we have the capital Fx, which actually eventually is going to become the indefinite integral, and the corresponding Fx. So we got to write some functions here under Fx, derive it and write the answer as lowercase fx, right? But actually this is not the function we know. We are going to have problems of the lowercase fx for which the corresponding integral can be taken and used in the rest of the computations. So let's write some values here. X power n, if you take for example, we already differentiated that and we found the value as nx to the power of n minus 1. Very simple. So that means our interest is not differentiating x power n. Our interest is in integrating something which looks like x power n. I have written n minus 1 there, but actually we want x power n actually. And this n also I don't want. Actually what we want as fx is x power n. I want to integrate x power n, really, that is my interest. But unfortunately integrating this function, plotting and integrating is difficult. So we back calculate that. So what will be the corresponding fx is the power is one extra power is there. So will be x power n plus 1. But that introduces a factor n plus 1 that side, we have to divide that by n plus 1. So x power n plus 1 by divided by n plus 1. If you differentiate, you will get x power n. Actually the same formula. Of course, one simple thing, when you make a statement like that, you always look for exceptions. There is one exception to this. N cannot be minus 1 in this case or 0 in this case. If n is 0, x power 0 has no, you can't derive, that is a constant, no? X power 0 is 1. So this first statement itself is valid only when n is not equal to 0. So you should remember that. So this case is n is not equal to 0, correct? But we have practical situations where we want this to be integrated, where n is actually 0. No? That means x power minus 1. So actually we are interested in 1 over x. 1 over x is not covered in that. That's the only exponent of x which is not covered by this statement is 1 over x. Otherwise x power n handles even 1 over x squared will be handled, no problem. 1 over x cubed we can treat that as x power minus 3. But 1 over x we can't treat that as x power minus 1. Because x power minus 1 plus 1 will be 0 there. So 1 over x is the exception there. And what is the integral of that? That is, what is the function when we differentiated, we got 1 over x as the answer, derivative, no? I don't know if you recall, is log x. Log x written as ln, natural logarithm. So natural logarithm, when you differentiate, you get 1 over x. So that is the exception. So now any power of x we can take. If it is 1 over x, use ln x. If it is x power n, use x power n plus 1 by n plus 1 as the integral. So we can find the integral. Similarly, we have seen sin x, for example, cos x. That means actually if you want to integrate cos x, sin x is the answer. Whereas if you want to integrate sin x, what do you have to differentiate? Not cos x, minus cos x. Because cos x, when you differentiate, you get a minus sin x. Therefore, you have to differentiate minus cos x to get plus sin x. So this is a trigonometric function, two functions I want. And you can write a few others if you want. Like e power x is known. E power x is e power x. I mean, there is no doubt there. Both are same. And if you look at tan x, we get secant squared x. I don't know where you want to integrate secant squared x in life. If you need to integrate it somewhere, integral is tan x. We don't know. Similarly, if you want to integrate cosecant squared x, I have no idea when, will be minus cosecant x. Or if you want to integrate secant x tan x, not secant squared x. Secant x. That is, what we do is, we keep differentiating as many functions as we want and write their corresponding differentials, derivatives on the right side. So we make this table and we keep that as a hand table. It is available. Anytime we want to integrate some long expression, we will compare that, parts of that long expression with different values that you see here. And then see we can match it. Then we can integrate. I will take one simple example of that method, which will also take us to the next topic in our discussion. or I can do that later, doesn't matter. We can look at some actual practical examples of when we require these definite integrals. One was, remember, Newton was interested in calculating the planetary positions, that is the data movement of an object. Actually, we are interested in movement of an object. An object is there at one point in space. After some time, what is time? Itself is the axis, no? Time. Time is the axis. So this is 0 time. Starting at one point, that is a 0. Now is a 0. The object is somewhere in space, right? And after some time, at time t, where is this object? It has moved, no? Maybe it has moved. What is that position? So that means we are looking at this position of an object as a function of time. Like we write f of x. Function is position. Function name is position. Independent variable is time. F of x is position of time, or you can write it as p of t. Write that. Like for example, at 0, what is the position? P of 0. At time t, what is the position? P of d, like fx, no? P of t, correct? So what will be the value? Is the question. Of course, the first case is object is not moving anywhere. Stationary object. That is the Newton's first law, which says that an object which is stationary will remain stationary, correct? It doesn't move anywhere. So therefore, whatever the initial position of P0 was, will also be the same at position time also is same as P0. Final answer is P0 only, correct? Simplest case. The next case is the position is changing with time. There is a rate of change of position. So we have velocity or speed. Speed in one direction, we call it velocity. In this case, we just take it as velocity. So velocity is there. If velocity is there, position keeps changing, right? So we look at the different rates of change. We look at the different rates of change, correct? Now, what is the rate of change of position? If you recall, I had written 6 different rates of change. Just list those here. First one is velocity. The rate of change of position is called velocity. Actually, you can write it as P prime t, no? Like f prime x. Derivative of p with respect to time is p prime. P prime t is velocity. The next rate of change of velocity itself will be, that is known as acceleration, correct? And that is actually p double prime t. That is the acceleration. And rate of change of acceleration, we call it jerk. That will be p rate of change of position. That is the jerk, correct? Then we have snap, which is P4 of t, rattle, P5 of t, and pop is P6 of t. Of course, I have just written all the 6 here, but we compute for 1 or 2 here and generalize. No? That is our standard method of calculation. Let us assume there is a velocity. That means velocity at 0 will be there. So there is a P prime 0. So there is a P0. In addition, P0 is already there in Pt. Plus, because of the acceleration at 0, what is the change of position? Will be integral of P prime 0 dt from 0 to t. I will not write a separate variable here. I should call it du or something if you want, if you are confused. You have to integrate the, if you integrate the velocity, you get the distance moved. No? Yeah. Okay. No, I don't want to add this P0 here. We'll keep that one place. We know that P0 is there. In addition, the distance traveled because of a velocity. Similarly, third step will be distance traveled because of an acceleration and so on. We'll write those values separately and add all of them up. We'll get the final position, Pt, correct? So we'll do that. That's a good way of looking at things. So for velocity, if there is a velocity at 0, whatever velocity, then what is the distance traveled will be an integral from 0 to t, in this case p prime 0 dt. I have written the same variable name here. If you get confused, I will write a du or something if you think this is confusing. So I got a variable u, which is changing from 0 to t, and we are integrating p prime 0. I am assuming acceleration, jerk, snap, rattle, pop and everything else below. Everything is 0. So that means this velocity is constant. The starting velocity p prime 0 is there, is constant. So I can take it out of the integral and I can write that as p prime 0 multiplied by t. That will be the integral. Indefinite integral is p prime 0 t. We have to evaluate between 0 and t. If you want, I can write that step separately, which will be the same as p prime 0 multiplied by t. Because at 0, the value is 0. So now let us assume that there is an acceleration also at, there is an acceleration. Velocity is there or not there is already taken care of. But velocity may actually change because of the acceleration. So we have an acceleration at 0, which means what is the velocity at the point t? Will be integral 0 to t of p double prime 0, which is the acceleration at 0. I will write that as dt only. Doesn't matter. We understand. I should write a different variable name. Doesn't matter. So this integral from 0 up to time t, if I can calculate, that will give me the velocity at time t, which means the distance travelled will be, we have to integrate this velocity from 0 to t of dt. Correct? No? That means I already have value for this. I can take that and integrate that. Will be equal to, I can write that here. Integral 0 to t. So we calculate the inside integral first, which is practically the same as this, but p double prime 0 is there. So that will be p double prime 0 of t, that is the integral, dt. This will be, so we integrate this, will be p double prime 0, t dt will be t square by 2. We got that. We got our table there. No? So that's the purpose of that table. No? So, t square by 2, which is fine. So next we go to the fourth step is now we have a jerk also. That means acceleration itself can change. There is a rate of change of acceleration which we call a jerk, correct? So which means the distance travelled will be now, first we have to integrate the velocity, then we have to integrate the acceleration. You understand? That is, we integrate first time we get acceleration, that you integrate you get velocity, that you integrate you get position. So 3 times you have to write it. So 0 to t, integral 0 to t, integral 0 to t of p triple prime 0 of dt, dt, dt. Correct? This will be the distance travelled, will be equal to, I am going to skip all the intervening steps and write the answer. Now you can see the inner part is same as what we had earlier. Only difference is we have p triple prime 0 instead of double prime 0. So that means the value of this inside part will be p triple prime 0 t square by 2, which we have to integrate now, which will be p triple prime 0 t squared by 2 has to be integrated. T squared will give me, integral will be t cube by 3. So the 2 is still there. T squared integral itself is t cube by 3. So therefore it will be t cube by 3 into 2, which is actually t cube by 3 factorial if you want to write it like that. So p triple prime. So now supposing fifth, we have a snap also. I got a fourth level derivative is there, which means I have to integrate it 4 times. So that will give me a distance moment of p to the power of 4 0 multiplied by integral of this will be t power 4 divided by 4 multiplied by, of course, we had the 3 and 2, you have to retain that. Correct? So now we can write the final answer. So what is PT? Assume we are going to have jerk, snap, rattle, pop, blah, 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 blah. Any number of derivatives in life. Infinite number of derivatives are there. Assume that. So that means we are going to write infinite number of indefinite integrals, integrating one inside the other and adding all of them up, right? So what will be the value? We just add all the values which we, for each distance that we got, will be equal to p of 0 plus p prime 0 of t plus p double prime 0 t squared by 2. I'll cheat and write that as 2 factorial plus p triple prime 0 multiplied by t cube by 3 factorial plus p4 of 0 multiplied by t power 4 by 4 factorial. This much I already have. I think the rest also we can write. P power n 0, not p power n, p n 0, nth derivative at 0 multiplied by t power n by n factorial plus etc. It will keep going. No? If you do it till infinity, as long as derivatives are there, this will evaluate the value at t. So that means what we have really achieved, that just think back in this whole picture, we had a position at 0, known position, which is p0. Now we wanted a value for the position at a time t. How do you find that? If you know all the n degree differentials at 0, all the differentials, derivatives at 0 to any degree, if you have at 0, it should be possible to calculate p of t. That is the equation. And this equation is known as, it's got a name. Actually, let me just rub this part and discuss a part of history of mathematics which relating to this. Okay. This equation itself is called Maclaurin series. That's the name. And even though we derived it for a position with respect to time, you can see the whole derivation is same. Even if you had a function of x, correct? No, function of variable x. I want to calculate the value of fx at any value of x. If I know the value at 0 and all the derivatives at 0, I can compute the value of fx, correct? No? So fx equal to f0 plus f prime 0 multiplied by x plus f double prime 0 multiplied by x squared by 2 factorial plus etc. I will write one nth term f of n 0 multiplied by x power n by n factorial plus etc. till infinity. This is known as a Maclaurin series. It was used massively by one English mathematician, Scottish mathematician called Maclaurin. So they call it Maclaurin series, but actually it's a generalization of a related series. Now here we use the value of the function at 0 to compute the value at any x, right? So many times that may be correct also, but if you say I got the x-axis and 0 is the point, I want the x-axis. I know the value of f at 0. I know the value. This value is known. At some x is what we are trying to find, correct? At some x, I want to find the value of x. So how do you find it? Is all the derivative is 0, I know I can find it. No? Yeah, but the problem is this may not work if there is too many wavy part of the graph. No? So that means it will probably work in the neighborhood of 0. That means my x is very close to 0 on either side. Probably this got a better chance of working, correct? No, because small distance, small time traveled, it will be correct. Whereas the farther I go, lesser chances that this is going to work, which means now instead of 0 as the reference point, we would like to use a neighboring point. Let us say I've got a point here called A. I know the value of function at A. I know fa. And I know the derivatives of the function at A. I know f prime A. I know f double prime A. Just like 0. Instead of 0, point is A. Neighborhood of A, if I calculate, it's got a better chance of converging, right? So now how do we do that? The same, practically the same integral, except that instead of 0 to x, we are writing a to x. From a we integrate. From a we integrate that a to x. So I'll write one such value for the first order derivative. Then we can generalize the same thing. Simple, straightforward. So supposing f prime a is non-zero, that means first order derivative is non-zero. How do you find a second? How do you find a position? We have to integrate from a to x of f prime a dx, correct? Which is equal to the x itself. F prime a is a constant. F prime a multiplied by x, but now you have to evaluate from a to x, not 0 to x, which will be f prime of a multiplied by x minus a. That's the only difference. Instead of x, we have to write x minus a. And when we integrate this once again, this becomes x minus a whole squared by 2 again. It's the same, there is no difference. Because when you say I differentiate x power n, I get nx power n minus 1, correct? This is what was there in our table. Supposing I differentiate x minus a to the power of n, what will I get? I'll get this is like a function of a function, no? Something to the power of n will be something n multiplied by that same thing to the power of n minus 1 multiplied by derivative of that something, which is 1 anyway. So it will be nx power n minus 1 anyway. So it's the same. The correspondence is the same whether it is x or x minus a, which means now we can write one more series, which is f of x given the values of the function and its derivatives to any order at a point A, what is the value at a point X which is in the neighborhood of A will be equal to Fa plus F prime A multiplied by X minus A plus F double prime A multiplied by X minus A whole squared divided by 2 factorial plus F triple prime A multiplied by X minus A cubed by 3 factorial plus etc. General term you can write Fna multiplied by X minus A to the power of n by n factorial plus etc. That's the series. And now this series was actually derived by our friend was a Brooke Tyler. A British mathematician. Somewhere around, I think, 1669 or something. No, that's the year when he found it. Maclaurin series, Maclaurin used in, I think, 1700 or something, later actually, but anyway, it doesn't matter. Actually, if you set A equal to 0, that is same as Maclaurin series. Now, around 1671 and 1673, that means in a period of 6 years, you can see, or 4 years, 2 other friends formed the same series. Right? One fellow is known as Newton, another fellow is Leibniz. Correct? Now what we will do is, these are called those names, that is correct. But now I'd like to take one actual example for which we have done good amount of work to differentiate and find the derivatives of any order. If you recall, we differentiated sin x, what did we get? Cos x. And differentiate cos x, what will you get? Minus sin x. Differentiate that minus sin x, what will you get? Minus cos x. Differentiate that minus cos x. See, that means I can differentiate any number of times. We have already done it, but then we apply that. So, very simple. One example, we can apply Maclaurin series itself instead of Taylor series at 0 itself. I will apply that for our function which is sin x actually. So, what is sin x equal to? So, our fx is sin x. And what is f prime x will be cos x. F double prime x is minus sin x. F triple prime x is minus cos x. I won't write anything else because that again comes back to sin x. So I just need 4 values here. So what is the value at 0? X equal to 0. Or x is, you set the value of x as 0. So what is f0? Sin 0 is 0. What is f prime 0? Is cos 0. That is a 1. And what is f double prime 0? Is minus sin 0. Also 0. And what is f triple prime 0? Is minus 1. Right? And what is f4 0? Back to 0 again. So it repeats 0, 1, 0, minus 1, again 0, 1, 0, minus 1, 0, 1, 0, minus 1. These are the derivatives of sin x. Therefore, now we can write the sin x expansion, sin x as a infinite series, right? f0, I won't even write it. It's 0. You can write 0 if you want, 0 plus, you know. And what is f prime 0? Is 1 multiplied by x. F prime 0 x. See there. I am just substituting these values of the different derivatives in this Maclaurin series. X. And what is f double prime 0 for x squared? is 0. We won't even write it. And for x cubed, f triple prime 0 is minus 1. So it will be minus 1 x cubed by 3 factorial plus power 5 by 5 factorial minus, I can write that, etc. Write the infinite series, no problems. Now we'll do the same thing for cos x also. Supposing fx is equal to cos x, and what is f prime x will be minus sin x. This actually I've got the values here. And f double prime x is minus cos x, f triple prime x is sin x. And that repeats here again, f4x will be cos x. And so our interest is the value at 0. So what is f0? Cos 0 is 1. What is f prime 0 is sin 0 is 0. What is f double prime 0 is minus cos 0, which is minus 1. And f triple prime 0 is sin 0, which is 0. Now substitute these values repetitively in this Maclaurin series. So what will be our cos x? 1, f0 is 1. Then f prime 0 is 0, so second term won't be there. It will only have even powers, you can see. X squared is there, but that will be with a minus sign. So 1 minus x squared by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus minus even powers. This is a cosine series. No? So this is a trigonometric infinite series for sin x and cosine x. So because they were discovered by Newton and Leibniz almost around the same time, they are actually called Newton series and Leibniz series. And there is one more series for arctan x. Arctan x is, we'll take that as a separate example. Arctan x is what we normally use to write as tan inverse x. Tan inverse x. In fact, this practice is not very popular. We write that as tan inverse x, inverse function of tan. Arctan is a more popular notation. There is one more series for it, which was, I'll write the answer here, but I'll not show you the actual derivation, will be x minus x cubed by 3 no factorial plus x to the power of 5 by 5 no factorial. There is no factorial. See, there is a difference between sin and arctan. There are no factorials here. It is just plain numbers. 7 plus etc. This series was discovered by a gentleman called Gregory. So it's called Gregory series. So I got Gregory series here. I got Newton series and Leibniz series here, right? These are all approximately discovered in the 17th century by the European mathematicians. But then 200 years earlier to that, that is the 15th century beginning, we had one friend called Madhava. From the Kerala School of Mathematics, around, I'll just write the data, around 1420 or something. 1400, he actually gave all these series before calculus was invented, before anybody knew what is a differential, what is integral, what is definite integral, what is indefinite integral. Was not even known. Calculus as a subject didn't exist. 200 years before that, you see. Calculus came into existence around 1670, that's the time, correct? Our friend is more than 200 years earlier, he discovered these infinite series which are actually based on calculus. Really, this is based on calculus. That's why I think historians have agreed to say This should not be called just Newton series, it will be called Madhava-Newton series. The first name credit goes to Madhava. It's not Newton-Madhava series, it is Madhava-Newton series. Or you can call it, you want to give equal respect to Leibniz, you can call them Madhava-Leibniz series. Both sin x and cos x, they are called Madhava-Newton series or Madhava-Leibniz series. And the Arctan x series should be called Madhava-Gregory series. In fact, this Madhava-Gregory series, nobody was actually interested in tan inverse function as such. Their interest was in calculating value of pi, which is the ratio of circumference of a circle to the diameter. And we know that tan 45 degrees is 1, no? Tan 45 degrees is 1. Everybody knows that. Opposite side by adjacent side is equal when the angle is 45 degrees, because the right angle triangle becomes isosceles. If you see the right angle triangle, when one angle is 45, another angle also will be 45 only, because this is 90 degrees, right? So for this 45 degrees, opposite side and adjacent side both are same. So cot 45, tan 45, both are 1, right? 45 degrees, we don't write that as 45 degrees, we write that as tan pi by 4. Is 1. Which means pi by 4 is arctan 1. Therefore, what is pi? Or I can write pi by 4 itself, or you can write 4 itself. 4 multiplied by arctan of 1. Substitute x equal to 1 in this series, will be 4 multiplied by 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus etc. You add a sufficient number of terms, you will get a sufficiently accurate value for pi, of course. It's correct. But then this series is so slow in convergence that you need to add, let me just make the observation, 5 billion terms of this to calculate value of pi correct to 6 or 10 decimal places. If you want, you will need to add 5 billion terms. So they are very slow converging, but then in those days, 1000 years ago, they wanted some. Remember, we have used pi as a 22 by 7, correct, no, in our geometry class. You get 22 by 7 just by adding some 5 terms here, so no problem there. So it is accurate to that extent, but then if you really want very accurate pi, you cannot use this. It's a very slow convergent series, okay? Now, I can give you some alternates for this if you want, but then that is different. Now, we'll have to, I'll take a small break here, then we'll come back as a continuation of this topic.